Thank you everyone for coming today. So today I'd just like to introduce the SMILE mission and some of the exciting science that will be going on or is going on at Leicester right now, and when we launch in 2025 will continue here at Leicester. And so Leicester has this really special position within the SMILE consortium. We're building one of the instruments and we're also heavily involved in the science and the science exploitation. But before we get there, I'd like to give you a brief introduction of how the SMILE mission came about. So as you know, in this department, we have a strong heritage in X-ray astronomy, and this has led a group of X-ray astronomers to move into solar-terrestrial physics, which has been a really nice journey. So I'm going to start in the ROSAT era. So this is late 1990s. ROSAT was a satellite launched by MPE in Germany, and it wanted to do lots of things, including a whole all-sky survey of the X-ray sky. But one of the observations it made was of the moon. And you can see there's a large image of the moon here on the screen. So on the day side, you can clearly see the sunlight, the sun glow of the moon here. But on the night side, where we'd expect zero photons, we have quite a few. Now, this is after any instrument cleaning, etc. We think this is clean data, and we've still got a couple of photons that are visible in the image. I want to highlight the work of this one individual. There's lots of people that have worked on this field, but this is one of the major players. So in this room, even we have many SMILE people in the team, but one of the people that made a large contribution to this field is Steve Snowden. He's now retired. He used to be at NASA Goddard, but earlier in his career, he was at MPE working up ROSAT data. What he wanted to do and what he eventually did was produce one of these amazing maps of the X-ray sky. So this is an all-sky image, and you can see it's a nice data set that's been published and well cited, and that's really great. But he did have this problem. This problem at the beginning. He tried to make this map, and he saw these streaks in the data. So he stacked up many observations of ROSAT to make this map. And you can see these streaks going through the sky. This is obviously not physical. It needs to be explained or not expected. It's not the X-ray astronomical sky. It needs to be explained. So he called these streaks long-term enhancements. Then a colleague of Steve's, a guy called Tom Cravens, who was working at the University of Kansas, just plotted a time series of the X-ray counts from those long-term enhancements on the ROSAT map with, you can see here, and also plotted on the same time series what was going on in the solar wind. It might seem obvious to people in a solar terrestrial field to do this kind of thing, but for X-ray astronomers and other people, we don't normally consider anything going on in the solar system. And you can see that there's a nice lineup of when X-rays, we have high counts of X-rays, we also get high solar wind flux rates. Around sort of the same era, ROSAT also had a look at the odd comet or two. And part of the same team, it was very much a small group of people looking at these objects, were thinking about what was causing this X-ray emission of the comets. The theory that came out of this was that this was called a solar wind charge exchange X-ray process, whereby some sort of ion, a heavy ion, so this is a nucleus that's bigger than helium, can steal an electron from a hydrogen atom, a neutral hydrogen, and in doing so, after the relaxation of that electron, we can have a photon emitted. Now, because of the ions that were involved in this process, then that photon happens to be in the X-ray regime. So we have this solar wind charge exchange emission process, or SWIX for short, and I'll be calling it SWIX from now on. Now, ROSAT did its thing, and then a bit later on, XMM was launched in 1999 and it's still going, and there's lots of heritage in this department with XMM. And this is when I started my career in astronomy. I'm there. This is a team of calibration scientists. We've got Andy and Steve in the room as well. And you can see Steve Snowden's up there as well. So Steve Snowden moved on from ROSAT to XMM. So XMM is orbiting around the Earth. X-ray satellites are in orbit, and it has a large orbit that takes us a long way away below the ecliptic plane in this Z direction. It takes about 48 hours to do this orbit, and it turns off around perigee as well. So that's another thing to remember about this. But XMM was also seeing sort of the same sort of problems, if you like, what ROSAT was seeing. And XMM has a very narrow field of view, about half a degree across. So it's a pencil beam And it's looking at its astronomical target, whether that be a star or a galaxy. But it also will look at anything in the foreground. So we've got various types of background. We actually call it background because it's easier. We have unresolved AGN, for example, the local bubble, the local galaxy can emit in X-rays. We also have components nearer us. And it turns out that this is the reason why we're seeing those excess photons in the ROSAT image and those long-term enhancements in the all-sky map. The exosphere is a region around the Earth that we have taken one image. This is an image from the Leica instrument on a Japanese satellite called Procyon, I think is how you pronounce it. Its mission goals were to look at an asteroid, but it did turn around and an ultraviolet image of the Earth's exosphere. So it was a one snap of what we've got. So you can just see this big cloud, and this ultraviolet emission is detecting that neutral hydrogen. So it's large. So we often in the solar-terrestrial field draw pictures of the Earth's magnetic field, which you can see here. And I hope you can see some sort of diffuse cloud that's around it. Now, the diffuse cloud is representing the exospheric hydrogen, which doesn't feel the field. But what we do have coming in is these ions from the solar wind, this really heavy ion. So oxygen 7+, oxygen 8, for example. So these are atoms that have had more or less all of their electron strips. They might have one left or none left. And also we get some carbon as well. That's quite common, some nitrogen. It's a very small percentage of the solar wind. It's about 1% of the solar wind is one of these heavy ions. A lot of work goes into what's going on with electrons and protons, but I don't think we can forget this 1% of that solar wind. So if we think about that solar wind interacting with that hydrogen, then we might expect X-rays to be mainly emitted in the sort of darker pink regions. Now, it's a bit more nebulous than this, but we're hoping that we can then see we are detecting these X-rays from the magnetosheath. So this is that darker pink region that you can see. So it's outside the Earth's magnetic field, and it's where that solar wind is coming in and interacting with the hydrogen. Now you see that XMM, I've just done a sort of cartoon of where XMM would be looking through. It's quite dependent on date and orbital dynamics about when we can actually see through that dayside region of the Earth's magnetic field. And so in my PhD, I went and tried to work out how much of the XMM archive at the time was affected by this SWIX emission. So this is work I did with Andy and Steve, who are in the room. And we preferentially detect when XMM was looking through this dayside, what we call the nose of the magnetosheath, where it pinches at the front. We also saw an effect with the solar activity. We used the solar sunspot number there as a proxy for the activity, and you can see that it generally is decreasing across that time series. And you can imagine a decrease, well, not imagine, I can see it, a decrease in the number of detections of SWIX emission that we saw in the archive, with a strong dependence on detecting these in summer. And that's because XMM can only look through certain parts of the magnetosheath at certain times of the year. So we're seeing these peaks in the blue, which is the summer observations. And when we do look in more detail at a particular case of SWIX emission, we can identify those particular ions that are within the solar wind. So we do this using X-ray fitting with, we have a software package called XSpec, which is commonly used. This is a typical plot that you get in X-ray astronomy. So you've got energy at the bottom, and you can see the counts rate at the top. We model out various components, so we have to get rid of the sky. So some of those lines there are to model out the astro sky. We're not interested in any of the AGN or anything like that. And then we add Gaussian lines to the spectral fitting to identify those lines. This is a particularly good example. This is when we think we've seen a coronal mass ejection coming from the sun passing by the Earth, and we can see this incredibly rich spectrum. So with our collaborators in the States, so the people in NASA, we were invited to work on an initial proposal. What if you could take this idea and image what's going on in the Earth's magnetosphere using these X-rays? So there was this idea back in 2007 to image the Earth's magnetosheath using this SWIX emission, but from a lunar-based observatory. This was going to be astronauts were going to go back in about 2010-ish, and they were going to stick a suitcase-sized telescope, press on and go, and then we'd be able to get some sort of movie, as you can see on the right. Now, in the end, that didn't happen, and I didn't think it was the right time, but we did go to some fun conferences. Buzz Aldrin was at one of them. That was an interesting experience. And then that got rejected, and we tried again with ESA in something called their medium class. And we tried again this idea through NASA, also through ESA again, reworking this proposal, making it smaller and cheaper. And then eventually, the idea to use this fixed emission to image the magnetosheath was selected by the European Space Agency and the Chinese Academies of Sciences back in 2015. At the time, we were going to launch in 2021. That's obviously not happened, but that's the way it goes. So it was all hands to the pump, because that's not very long to build a spacecraft at all. So what we're going to do is we're going to get through, hopefully, image what's going on. We'll take real pictures instead of using these animations. Now, we can see this great animation of a CME coming for the solar wind, hitting the Earth's magnetic field and rearranging those field lines. But you can imagine that this is the simulation that we've taken from something similar on the movie to the left is actually going to be a real image. We're going to get something smaller than that, but we're going to really take those first images of what's going on out in space. So that SMILE will launch in 2025 from